Okay, good morning, class. Today's lecture, we continue looking at quadratic equations, but this time look at equations of quadratic form. So, an equation such as x to the power 4 plus 5x squared minus 36 equal to 0 is not a quadratic equation. It's not a quadratic equation. However, if we let say m equals x squared, then this equation star can be written as we can write this as x to the power 2, the whole thing to the power 2, plus 5x squared minus 36 equal to 0. But using the fact that m is x squared, so that will mean we have m squared plus 5m minus 36 equals 0. Then this can easily be recognized as a quadratic equation in M. So we think of factors of minus 36, which are integers, such that when you multiply them, you get minus 36. When you add them, you get 5, which is the coefficient of M. You see that this will give us, or we can think of 9, then minus 4. When you multiply these two, 9 times negative 4, it will give you 36. When you add, it will give you 5, which is the coefficient of M. So I can write this equation as m squared plus 9m minus 4m minus 36 equal to 0. Then so if we now factorize in pairs, we end up having m plus 9 minus 4 plus 9 equals 0. You see that from here we have m plus 9 into m minus 4 equals 0. But the product of two numbers is 0 if at least one of the two numbers is 0. So this means m plus 9 is either 0 or m minus 4 is 0. But when you solve this, from this m will be minus 9 or m will be 4. But remember, this is a quadratic equation in M. Our original equation is in terms of x's, so we have to go back. And work out this in terms of x's. So say since m is x to the power 2, we are going to have x to either x to the power 2 is minus 9 or x to the power 2 is 4. But when you look at the first case means x is equal to plus or minus square root of minus 9. And the second case gives us plus or minus square root of 4. But the square root of negative 9 is not a real number. We are only interested in real solutions. So this is not a real number. So the only possibility, so we can just say, note that square root of minus 9 is not a real number. It's not an element of R. It's not a real number. It's not a real number. So if it's not a real number, we'll forget about this part and just consider, we therefore consider only x equal to plus or minus square root of which gives us plus or minus 2. Maybe we can just check these solutions in the original problem. We check those solutions in here. You see that when x is minus 2, you see that the left-hand side is going to be minus 2 to the power 4 plus 5 minus 2 squared minus 36 equal to 0. And this to give us 16, that is 4 plus 20 minus 36. You see that this is 36 minus 36 and gives us 0. 0, which is our right-hand side. Therefore, x minus 2 is indeed a solution. Is indeed a solution. So next, we check when x is 2, where left-hand side will be 2 to the power 4 plus 5, 2 squared minus 36. Let's see what we get. That will be 16 plus 20 minus 36, which we know is again 0. Therefore, x equal to 2 is also a solution. Hence, the solution set S dot S, it is the set with minus 2 and 2. So that's how that can be solved. We can look at another example. So this one, second example is example 2. Says solve x to the power 2 over 3 plus x to the power 1 over 3 minus 6 equals 0. Again, this can be, when let P be x to the power 1 over 3, then x to the power 3 is going to be p squared. So therefore, we have p squared plus p minus 6 equal to 0. Then we simply look for factors of negative 6 whose sum is 5. Those factors, I think, 3 and minus 2. When you multiply 3 and minus 2, you get negative 6. When you add them, you get 1, the coefficient of p. Therefore, we can decompose our p as 3p minus 2p minus 6 equal to 0. And then factorizing in pairs, we have p plus 3 minus 2p plus 3 equals 0. So p plus 3 into p minus 2 equal to 0. Then solving this resulting equation as before, we have either p is minus 3 or p is 2. But your p is chosen to be x to the power 1 over 3. Therefore, we have either this is minus 3 or x to the power 1 over 3 is 2. Then solving this separately, we have x is equal to, here we have to raise to the power 3 both sides, minus 3 to the power 3, that's minus 27. Or x is equal to 2 to the power 3, which is 8. So, but we have to check the solutions. We have to check the solutions. We have to check the solutions in the original given equation, which is this one here. So let's do that. So when our x is minus 27, the left-hand side of the given equation is going to be minus 27 to the power 2 over 3 plus minus 27 to the power 1 over 3 minus 6. But this is cube root of negative 27, which you know is negative 3. And when you square that number, you have 9. Similarly here, we have minus 3, then minus 6. 9 minus that is 6, 6 minus that, it is 0, which is the right-hand side. So therefore, this is one of the solutions. When x is 8, let's see, left-hand side of the given equation is going to be 8 2 over 3 plus 8 to the power 1 over 3 minus 6. And this is going to give us, taking the cube root of that, which is 2, then square 4, plus the cube root of 8, that is 2 minus 6, and this is also 0. So therefore, our solution set is the set with minus 27 and 8. So let's see what we get there. Okay, next, another example 3. It says solve 15x to the power minus 2 minus 11x to the power minus 1 minus 12 equal to 0. Okay, this one, you note that 15x to the power minus 2, you can write this as 15x to the power minus 1, then squared. Okay, therefore, I can let x to the power minus 1 be t, so that I have 15 15p squared minus 11p minus 12 equals 0. So this one, if you check nicely, we can use the quadratic formula. P will be minus 11 plus or minus 11 squared minus 4 times 15 times minus 12. Then you can divide this all by 2 into 15 to give you 11 plus or minus square root of 841 over 30. So we have P either is minus 18 over 30, which will reduce to minus 3 over 5, or your P is equal to 11 plus 29, which should be 40 over 30, and this will reduce to 3 over 4. Okay. So therefore, we have x to the power minus 1 will be equal to minus 3 over 5, or x to the power minus 1 is actually 4 over 3. So taking the reciprocal, this one will mean your x is just minus 5 over 3, and this one will mean your x is 3 over 4. We can check that the solution set indeed as minus 5 over 3 and 3 over 4. So now we can move on to the range of a quadratic. The range of a quadratic. Okay, the range of the quadratic function. The range of a quadratic function. So we can utilize the discriminant. So recall that a quadratic function f is defined as f of x equals ax squared plus bx plus c, where a, b, c are constants with the leading coefficient not 0. And the zeros or solutions, or we can call them, let's say, the zeros or roots of f, which are x values such that f at those x's, it will give us 0. are given by, I think you will recall from completing the square, we found x is minus b squared minus 4ac over 2a. And recall that, and discriminant delta is just b squared minus 4ac. And we set the number of the nature of the roots, the nature of roots is determined by the sign of delta. So one, if the discriminant is 0, then there is only one real root, which is repeated. And if delta is greater than 0, then there are two distinct real roots. Okay, distinct real roots. 3, if delta is less than 0, there is no real solution. So we can use the discriminant to be able to determine the range of a quadratic function. Example. The first example says, find the range of the function f of x equals x squared minus 6x plus 1. Of course, for this argument is a real number. So all you can do is, step 1, write f of x as y, so that you have y equals x squared minus 6x plus 1. Okay, then step 2, just rearrange this so that you have x squared minus 6x plus 1 minus y, and this is equal to 0. So we have now a quadratic equation. Okay, so this quadratic equation, we can step 3 for a real number x delta, which is b squared minus 4ac, should be greater or equal to 0. Therefore, in our case, we are going to have b is the coefficient of x minus 4 leading coefficient, and c is this one. So that's your c, 1 minus y. This should be greater or equal to 0. And this, if you work out, it will be 36 minus 4, then plus 4y should be greater or equal to 0. And this will be 32 plus 4y, it should be greater or equal to 0. Solving this simple inequality, you see, therefore, where 4y should be greater or equal to minus 32, which will mean your y should be greater or equal to minus 8. Okay? So that's the range. Step 4, we can state the range. The range of f, Rf, is Rf, it will be a set of all real numbers y, such that y is greater or equal to minus 8. Okay, x squared minus plus. So good things. But we could alternatively we could determine the same by completing the square. F of x is equal to x squared minus 6x plus 1, right? By completing the square, you can write this as that, minus 6x plus, the coefficient of x is minus 3, half the coefficient of x is minus 3. You square this, subtract it, then plus 1. So this, you can write this as x minus 3 squared, and then you have minus 8. You can see, but note that x minus 3 squared is always greater or equal to 0. So meaning when x is 3, this will be 0. 0 minus 8. So this quantity, because of this fact, okay. So what we have, because of this fact, we can say f of x, which is x minus 2 squared minus 8, we can say that this quantity is always greater or equal to, there's a 3 here, is always greater or equal to, yeah, of course, the minimum is 8 minus, so it's minus 8. So meaning that this is always greater or equal to minus 8. And that is, okay, so we could arrive at the same thing, because this is always non-negative quantity. So it is minimum when x is 3. So for any replacement of x, this will be greater or equal to 0. Okay, so this inequality holds, which simply shows that the values that f assigns to x are always bigger or equal to minus 8. And it is giving us the same set. Okay, we now move on to Okay, now proceed and look at exponential and logarithmic functions. Exponential and logarithmic functions. So definition, we'll start with exponential function. So an exponential function, is a function of the form, f of x equals c to the power x there, where, of course, the base a should be greater than 0, but a cannot be 1, and we expect c, and c is not 0, okay, is non-zero. So if we let our c be 1, we end up having f of x will now be ax to the power x. This is called the base, and that is the exponent. So this is the exponential function of the base a. We can look at the graph. The graph of f of x equals a to the power x. So this is your x, this is your y. So we have got two cases where no, our a should be bigger than 0 and a should not be 1. So we can find out what happens when a is between 0 and 1, and when a is greater than 1, what happens? Actually, it happens that you see that when x is 0, this is to pass through 1 all the time. And you'll see that when x, we are restricting a to be greater than 0 because we want to avoid problems of, cases where this is negative and the power here, maybe it is 1 over 2. A negative number to the power 1 over 2 will not yield a real number, right? So that's why we have restricted it this way. And the graph, actually, you see that when your a is greater than 0, it will be an increasing function like this. And here it will be approaching. So this is the graph. F of x is a to the power x when a is bigger than 1. That's what we'll see. And of course, when a is between 0 and 1, we end up having this. This will be the graph. F of x is a to the power x when a is bigger than 0 and it is less than 1. So this, you can see that it is a decreasing function. It's a decreasing function when the base is between 0 and 1. And it is an increasing function for a greater than 1. And it's very easy to check here that in general, domain of f, which is df, is actually, as you can see here, it is defined for all real numbers. And the range of f, Rf, you see, it can peak, the graph is approaching 0, meaning that it can get us to y equal to 0, but it will not reach y equal to 0. However, it can take any positive real number. So the range, it is 0 to positive infinity. Remember, I've excluded 0 because the function will never hit the x-axis. So other properties of, you see that y equal to 0 is the horizontal asymptote. It's an increasing function, it's 1 to 1. Okay, and all those. So, remark. We observe that a function f, the function, the exponential function is actually 1 to 1. Hence it has an inverse function. Okay, so it should have an inverse function whose domain it is 0 to be 0 to infinity, and whose range it will be the set of all real numbers. So what we are saying here is that since it is 1 to 1, there must exist an inverse function such that that inverse function, its domain is the range of f, and its range is the domain. So we'll look at that function shortly. So since it is 1 to 1, recall recall that if a function f is such that f at x1 is equal to f at x2 implies x1 is x2, then f is 1-to-1. It's a 1-to-1 function. This happens. Equivalently, f is 1-to-1 if x, picking two different points in the domain implies that the images are not different. So we expect for 1-to-1 function, each image must have a unique pre-image. Each element in the range must have a unique element, must have the exact one element in the domain. So, using this part, what are we saying when we compare it to the exponential function? We are saying f of x equals a to the power x. So, since it's 1-to-1, then this is true. So, since f is 1-to-1, we expect, if we have f at x1, which is a to the power x, if this happens, then we expect x1 to be x2. That is, a to the power x1 equals a to the power x2 implies x1 is x2. So we are going to use this property to solve equations involving exponential functions. Example. So examples A says solve 3x to the power 3 to the power x plus 1 equals 1. B 4 to the power 2x minus 1 equals 8 to the power x plus 3. C, we have e to the power minus x squared equals e to the power x whole squared into 1 over e to the power 3. So I'll start with the first one. The first one, because we are supposed to use this fact. I think we are starting with this, then we can compare the powers. So we have 3x to the power 1 equals 81. We can write it as 3 to the power 4. Yes, 3 to the power 4. And you have got the same base. Same base. You see, that's what we are saying here. Same base. Same base. So we can use the fact that the exponential function is a 1-to-1 and it satisfies this. It says whenever this happens, then the exponents must be the same. So, and this is going to give us 3. So your x is equal to 3 there. B, we have 4 to the power 2x minus 1 equals 8 x to the power 3, but I can write this as 2 to the power 2 and 2 to the power 3. So same base, we can, if this happens, then 2x minus 1 should be 3x plus 3. Okay? And when you work out your 4x minus 2 equals 3x plus 9. Solving for x, this will be x equals 11. We can check that that is indeed the solution. For C, we have e to the power minus x squared. Okay? And the other side, you can write it as e2x into e to the power minus 3. So this we can write like this equals e to the power 2x minus 3. So same base, e is the number between 2 and 3. So we can therefore deduce that minus this should be equal to 2x minus 3. But this is the same as saying x squared plus 2x minus 3 is 0. Then we can factorize. We have 3 and minus 1. So 3 and minus 1. Then we can, oh, doctor. What time is it now? I wanted to record two lecture sessions. What am I on? Okay, how long do you want? But this one I don't know, because that will go. So let me take okay, let me just finish this one. Then when they are done, I'll be able to come through. So we have x here, x plus 3 minus 1, x plus 3 equals 0. So this will be x plus 3 into x minus 1 equals 0. And when you solve this, we have x is minus 3 or x is 1. So we have got two solutions here. You can just check to find out if those are correct. In the notes, I've given so many exercises which you can try to look at. Then, you know, I've said that an exponential function is 1-to-1, therefore it must have an inverse function. It happens that the inverse of this is called the logarithmic function. So let's look at definition, logarithmic function. So we say the logarithmic function with base A. Of course, I'd say where the A is greater than 0 and your A is not 1. Okay? So this one is denoted by f of x equals log to base A of the number x. Okay, so it's denoted by this and is defined by f of x equals log to base of x if and only if. So if you call this y, then it will happen that this is the power to which the base must be raised to. So these two are equivalent. So these two are equivalent. So when I say y is equal to log to base A of x, then I simply say the base when raised to the power y, it should give us that. Similarly, when I say A raised to the power y equals to x, we can write this as log to base A of the number. That's all. We should be able to move in either direction. So, graph of f of x equals, I can put y, just y equals log to base A of x. About the exponential function, you see that this it passes always through 1, 0, and it goes like this. Here it approaches that at infinity. This side it goes. This is y equals log to base A when your A is bigger than 1. Okay, so you see that it's defined for all positive real numbers. Remember, it's not defined at 0, and it happens that when your A, the base is between 0 and 1, the function comes asymptotically to that. That becomes the vertical asymptote, and here it goes like this. We can use broken lines here. So it goes like this. This is the case when log to base A of x, when A is bigger than 0 and is less than 1. So of course, you see that the domain of f, in this particular case, where we view our f of x is y, you see that the domain, it will take all numbers from 0 to infinity, and the range, you see this graph can take anything up and anything down and up, similar for the other one, so it will be all real numbers. This is the same as the set of all real numbers. That is the range. Now, when you try to compare exponential functions, they are actually inverses of one another, because we can demonstrate this. Note that f of x equals a to the power x, and g of x equals log to base a of x are inverses of each other. We can check this. F evaluated at g of x, we have g of x is log to base a of x, and in there it will be a to the power log to base a of x, and you know this is x. Similarly, g at f of x, it will be g at f of x, it's a to the power x, so this will be log to base a, or then a to the power x. We have this. Using the properties of logs, this we can write log to the, and this is just, okay, so we can see what we call the inverse function property. Therefore, the inverse function property is satisfied. The inverse function property is satisfied. So we can review certain properties of logarithms, which may not be very new to you. One, log to base a of xy is always equal to log to base a of x plus log to base a of y. 2 log to base a of x over y is the same as log to base a of x minus log to base a of y. 3 log to base a of the power, you can bring down this power here, and 4 log to base a of a is always 1. So these results follow without difficulties. So we end this session here. We'll continue next time.